Okay, so after this analysis, we found both the ground state wave function and the ground state energy. The ground state energy is 1/2 h bar omega. Again, omega is set by the spring constant and the mass. The ground state wave function is written here, and you see that it has a Gaussian form. Okay, and remember, to get the full wave function, you would multiply this by the temporal part of the wave function, which is just a oscillatory function, e to the I omega t, and excuse me, I had to sneeze there. And so let's plot the ground state wave function, and let's just see what this looks like. So what I'm showing on the left hand side here are the wave functions for n equals 1 up to n equals 0, let's say. In the harmonic oscillator, if you haven't already understood that, the index runs from n equals 0, the ground state, and then goes up in integer multiples. Okay, and so I'm showing the wave functions, and so this ground state wave function, which was the only one that we solved for, is a Gaussian. And then what can be shown by applying the raising operator to psi 0, you get psi 1. Okay, in fact, you get a sub 1 psi 1, and that is and then from psi 1 you can get psi 2, and so on and so forth. Okay, and so I'm just showing you qualitatively what it looks like. You'll have a homework problem for which you solve for the first few of these explicitly. Okay, but we know that they have to have alternating even, that is symmetric with respect to the center of the well, and odd, that is anti-symmetric solutions like this. If we take the wave function squared, that is the probability density. Okay, then we just get this form here. We have 1 antinode, 2 antinodes, 3 antinodes, and so forth. Now, one of the things that we noticed about the that we mentioned about the classical harmonic oscillator is that it is most likely to be found at the turning points, because that is where the string is maximally stretched or maximally compressed. Spring is maximally stretched or maximally compressed, because that's where the velocity is the smallest when the mass is turning around. And here, what we see in the ground state wave function is, in fact, that the particle is most likely to be found in the center of the well, away from the walls. Now, it gets tiring to draw these all by hand, and so I found a simulation which we can use to look at these wave functions and the probability densities more explicitly, and we can see how it varies with the shape of the potential, that is the stiffness, the slope of the sides, etc. Okay, so here's the simulation. All right, and what's highlighted now here in orange is this is the ground state wave function, and now we see explicitly that these successive energy levels are separated by a constant amount. And as I roll the mouse over each successive one, you can see that now we start with an odd wave function, an even wave function that's symmetric with respect to the center of the well. Then it goes to anti-symmetric, symmetric, anti-symmetric, and so on. And you can see how it drops off smoothly. And then if we look at the probability densities, then you'll find, again, you have this one peak in the center. Particles most likely to be found in the ground state. The particle is most likely to be found at the center of the well, not at the ends. But as we go up in energy, we see that the particle spends a larger and larger fraction of its time at the turning points, at the classical turning points. That is over here where the energy is equal to the potential energy. Okay, that's the classical turning point, and you see that the wave function peaks up in those areas, indicating that the particle is most likely to be found there. Okay, so I'll post this on our website so that you can play with this a little bit more. And that concludes our discussion of the harmonic oscillator.